So I forgot to record today's lecture, so I'm re-recording the lecture material, and I'll be going over what we finished from last class regarding steady state error. So last class, we basically derived steady state error for unity feedback systems, and then we looked at non-unity feedback systems where we got into equivalent unity feedback system form. Then once we're able to do that, we can then apply our test inputs. So the purpose of this is to get into that equivalent form and then look at that G equivalent transfer function and then apply a test input of a step, ramp, or parabolic. Depending on the system type, we can then identify if there's going to be constant steady state error or if it's going to be infinite, depending on the system type. And system type is dependent on the number of poles at the origin. So a number of poles for G of S at the origin. And the type 0 system would have 0 poles at the origin. Type 1 has 1 pole at the origin. Type 2 has 2 poles at the origin. So today we're going to continue on with steady state errors for disturbances. So let's say we have multiple inputs now in our system where we have a disturbance input and a reference input, then we can derive the steady state error with multiple inputs now. And this isn't the only form where you can have disturbance enter the system. We can also have disturbance enter the system at the output, as highlighted here. We can also have disturbances enter the feedback. Well, actually, these two systems are basically the same systems or very similar because the disturbance is affecting the output, which is being fed into the feedback. So it's not unique, but this is just one way of representing disturbance entering the model. So let's derive this. And first, we're going to define this past the summing junction, this signal, as D plus G1 times your error, E of S. And let's write that down. So our output, C, is equal to that G2 multiplied by disturbance plus G1 multiplied by error. And then if we look at our other summing junction, the error right here, E of S, the error is equal to our reference input minus our output minus C, where another way of writing C is equal to our reference minus our error. And then we plug this back into the above equation to remove C and to have error as our representation, as our output. We then get R minus E is equal to G2D plus G2G1E. And then rewriting our error, we get 1 plus G2G1 multiplied by E is equal to R minus G2D. Then we divide both sides by 1 plus G2G1, and we get this. 1 over 1 plus G2 of S, G1 of S, multiplied by R of S, minus G2 of S, divided by 1 plus G2 of S times G1 of S, multiplied by D of S. And actually, to write this, I like to write it as minus G2 divided by G1 times G2 plus 1. And we define this term here as our error due to our reference input, E of R of S. And then this is our error due to our disturbance, E of D of S. So this is error from reference. reference input. And then this is error from disturbance. Note that they both share the same closed loop poles. So the stability of error is dependent on the closed loop poles. And that the steady state value only exists then for stable systems. Because if we were to derive this closed loop transfer function, so the closed loop transfer function, call it T, it's going to be equal to G1 times G2 over 1 plus G1 G2. So they share the same closed loop poles. Okay, so then in this specific application, our E of R of S is equal to 1 over 1 plus G2 of S, G1 of S, where it's defined as error is the output divided by our reference input. And then ED of S is equal to minus G2 of S divided by 1 plus G2 of S, G1 of S, which is our error divided by our disturbance input. And to get the steady state value, what we do is we take this expression of error in the frequency domain, and then we apply the final value theorem. Apply final value theorem, where E at infinity is equal to the limit as S goes to 0 of S multiplied by E of S. And that's where we get this expression here. So if the disturbance is a step disturbance, meaning that, and let's say it's a unit step, then D of S is equal to 1 over S. And here we don't really care what the reference input is doing. We're only looking at the disturbance, the effect of the disturbance on error. Then we just apply our steady state equation. So as error at steady state is equal to the limit as S goes to 0 of S multiplied by E of S, which is going to be S over 1 plus G1 S, G2 of S, multiplied by R of S, minus S times G2 of S, divided by 1 plus G1 of S, G2 of S, multiplied by our step input, disturbance input. So these two will cancel out. So then we get E to disturbance of the error at steady state is equal to minus G2 of 0 divided by 1 plus G1 of 0, G2 of 0. So basically what I did here was that this is the definition of error. And then I plugged in limit as s goes to 0, and I get this form. So next, what I'm going to do is I'm going to divide up both the top and bottom by 1 over g2 of 0. And I get this. So g2's in the numerator cancel out, and I get this. 1 over g2 of 0 plus g1 of 0. Okay, so the reason I show this relationship here is that our goal is to, we want error due to the disturbance to be very small or 0 if possible. So very small or 0 if possible. So for it to be 0, for this to be 0, we need this numerator term, or excuse me, this denominator term to be infinity. Or we need this to be infinity. So either g1 of 0 is infinity, but that's not possible. This because it implies that the DC gain of g1 is infinity. It's not physically possible. Or g2 at 0 is equal to infinity. Oh, excuse me. g2 of 0 is equal to 0 because we're doing 1 divided by 0 here, which is infinity. And this is possible. The other scenario is we can increase the DC gain. We increase the DC gain of g1 of 0. So we increase the gain of g1, that makes this denominator term bigger. So 1 divided by a smaller term will make it smaller. Or 1 divided by a bigger term will make the error smaller. Or we can decrease the DC gain of g2 of 0. Where if we make g2 smaller, then this term will be bigger, and therefore error is going to be smaller. And intuitively, I hope that makes sense, because if the disturbance is going through this plant here, and if we make the gain of this plant smaller, then we're also making this disturbance smaller as well, because the output is going to be equal to g2d plus, let's call this signal x1 plus x1. So the gain of g2 is going to be, or the output of c2 of c is going to be directly proportional to the disturbance as well. So having a smaller gain will mean that less of the disturbance pops up in the output. So finally, we're going to talk about steady state error for state space systems. So let's say we're given a state space of a closed loop system. Then you can also use the state space representation instead to find the steady state error. So consider the closed loop system representation state space below. And here I assume D is equal to 0, but I'll actually derive a generalized form for steady state error for including D. So it's going to be more generalized than in the textbook. So we have the closed loop transfer function being this definition. And steady state error in state space is defined as this, where we have a simple unity feedback system and let's say the output's y, and we have u here, then we have this simple feedback system here. And this is going to be our E of S. So we know that from the transfer function definition, T of S is equal to Y of S divided by U of S. So then we get Y of S is equal to T of S multiplied by U of S. And when we plug in the definition of the transfer function from earlier, we get this. C times SI minus A inverse multiplied by B multiplied by U of S plus D times U of S. Then we plug this into above equation. We get E of S is equal to U of S minus this whole term here, C SI minus A inverse times B times U of S minus D times U of S. And we get this. We can pull out the U of S multiplied by 1 minus C SI minus A inverse times B minus D. And then we apply the final value theorem to get this form. So another way of representing it with T or with D with a non-zero D, we get this. Limit as S goes to 0 of S, U of S multiplied by 1 minus C SI minus A inverse times B minus D. And this is for when D is not equal to 0. It's a more generalized form. So if you're given a state space, you can also find steady state error using state space representation. So just some takeaways in this chapter. Steady state error exists only for stable systems, and this is dependent on the closed loop poles. When we derived earlier the disturbance, the error due to disturbance, even though the disturbance is coming from a different area on the block diagram, it's still dependent on the closed loop poles. Now, steady state error is evaluated when the transient response is 0. So if the system is unstable, the transient response will grow to infinity. So there is no steady state error. That's why it's only applicable to stable closed loop systems. And this is why the transient response is still dependent on the closed loop poles. So the transient response of the errors is still dependent on the closed loop poles. Feedback systems can reduce steady state error, and this is typically attained by increasing gain. And the system type of the open loop system will dictate the steady state error value. So remember, keep in mind if the system is a type 1, type 2 system, or type 0, and steady state errors can be found using the transfer function or state space representation. So that wraps up chapter 7. And we'll move on to chapter 8 on root locus techniques. And this chapter is probably the start of our very important material, because understanding root locus is crucial for understanding each component of a PID controller and what each component does. And it starts with root locus. So even though PID and compensator design will not be covered until chapter 9, this is the start of the chapter that builds the foundation for controller design. So we're going to be talking about chapter 8 on root locus techniques. And I guess the purpose of this chapter is to learn visually how poles move. And when I'm talking about poles, I'm talking about closed loop poles. So poles from closed loop transfer functions. And basically, the root locus is just a plot that shows the trajectory of these poles. So we can easily see a system stability drawing the path of the closed loop pole locations. So imagine if I had a pole zero map and I can see the open loop poles start here, or maybe they start here and then they just veer out like that. And each part of these points are points for the poles. So these are complex conjugate poles and they only go in this path here. Then I can see that this system will never be stable because the poles are always in the right half plane. These are the trajectory of the closed loop poles. Closed loop pole path trajectory. So that's what root locus does. It gives us a visualization of how our poles move. Personal take on this is that it's not really used outside of this class, but it is important to understand root locus, which will help you learn how each component of the PID controller affects your system. So if you're a controls engineer in the field and you're asked to tune the PI or the PD parts of your controller, root locus will give you an explanation of why you're tuning each component, like why you're changing the gain for the integral part of the PID controller or the derivative part of the PID controller, instead of just playing around and just seeing how it reacts. You will now learn why it reacts that way. So we're going to go through the introduction of chapter 8, then talk about how to sketch the root locus, then refining the sketch, and then we'll talk about generalized root locus, chapter 8.8. Start with the introduction and some definitions. So given the system below here, note here that we pull the gain out of G, so G now has unity gain. So we pull the K out, and this now has unity gain, where G of 0 is equal to 1. That's the purpose. And we have this feedback H, so we get this closed loop transfer function form. So in chapter 5, the open loop transfer function is defined as GH, but note here that because of this gain K added, or this gain K popping up here now, we redefine it as K times G times H. And then the closed loop transfer function is defined as Kg divided by 1 plus Kgh, because this here is your G equivalent. G equivalent is equal to Kg now. So this is just important notation for this chapter. Main reason why we pull the K out is because root locus is dependent on increasing or decreasing the values of K. And by doing that, we're basically affecting the pole locations. So the poles is when 1 plus Kgh is equal to 0. So solving for the roots of S, or solving for the roots of that polynomial equation, we can get poles. And that changes by changing K. So given the system below, so the same plot, let's use some notation now, where G is equal to NG divided by DG, H is equal to NH divided by DH. Then our open loop transfer function can be rewritten like this, where we have G of S represented here, and we have H of S represented here. This is actually an error. This should be NH of S, which has been corrected on the notes now. And basically, we're showing here that the closed loop transfer function poles is dependent on the open loop poles and the open loop zeros. And I'll derive that real quick. So we get the closed loop transfer function is equal to kg divided by 1 plus kgh. And then we expand that, we get ng divided by dg times nh divided by dh divided by, there's a k here, 1 plus k times ng divided by dg times nh divided by dh. And we want to multiply both the top and bottom by dg dh. And these will cancel out. And we get dg dh right here. So then we get this term now. And I want to note that the closed loop poles are made of two components. So closed loop poles is when dg of s multiplied by dh of s plus k ng of s multiplied by nh of s is equal to 0. And then if we look at 1 here, this is our open loop poles where dg of s times dh of s is equal to 0. And where our open loop zeros occur is when ng of s multiplied by nh of s is equal to 0. And the k here is just a multiplier that doesn't change the 0 locations. So the closed loop poles are made of open loop poles and open loop zeros, which will be important on how the root locus is drawn. And we'll go over that later. So the root locus is a graphical technique that gives a qualitative description of a control system's performance. So in MATLAB, we basically do this. We use the command rlocus and we put the open loop transfer function g of s, h of s in here, and we leave the k out because MATLAB, what it's going to do is it's going to multiply this thing by k and then draw the closed loop poles of, or just going to draw the root locus and vary k. So it's a very useful visualization tool because you can see if your closed loop poles will be in the left half plane and if it's basically shows if it's stabilizable with feedback. And this chapter is extremely important for compensator design. So chapter 9 with PID controller and lead lag compensator design. So finally, we're going to go through part of this example from the textbook, given a security camera system. So in the textbook, they gave a block diagram showing camera where we have an amplifier called K1. This input here is our subject position. So where we want the camera to be looking at. K1 is an amplifier. And then K2 is defined as the motor plus camera, which is K2 divided by S times S plus 10. So this is a type 1 system because there's one pole in the origin, and then the outputs are cam position. then we're going to feed this back because the camera needs to know where it's actually looking at compared to where it wants to look at. So we feed it back here. And then the amplifier just amplifies this error. So then we're going to combine these where we let k is equal to k1 times k2. And then now you can see that the closed loop poles is dependent on k. So one thing to note is that varying k changes the closed loop poles. Closed loop poles location. So I'm going to draw out the pole zero map. I'm going to draw two plots here. And we have the imaginary axis, the real axis. We go to -10 down to 0, -5 here. You go to 5j and -5j. And on the left one, we have a pole plot. I'm going to call my pole plot. And then on the right-hand side, I'm going to have a root locus plot. They're going to be similar. Then I'm going to create a table with different k values. I'm going to have pole 1, and then I have pole 2. So let's say I let k equal to 0 as my starting point. And ignoring the fact that this is just going to be equal to 0, we have s squared plus 10s, meaning we have a pole at -10 and a pole at 0. And then if I increase the gain of the system to 10, then I have a pole at -8.87 and a pole at -1.13. So I increase it to 20, I have a pole at -7.24 and a pole at -2.76. Then this is called the breakaway point. At k is equal to 25, I have repeated poles at -5 and -5. So up to gain of under 25, between 0 to 25, we have two real repeated poles that are unique, which means the system is overdamped. When we have two repeated poles, the system is critically damped. And then now if we keep increasing it, and then say 30, gain of 30, we get -5 plus 2.24j, -5 minus 2.24j. So we now have complex conjugate poles. And if I go to 50 now, we get -5 plus 5j and -5 minus 5j. Anyway, so this is where I'll leave off for today, and we'll pick back up on completing this plot tomorrow. Thank you.